Welcome, everybody. Good afternoon. My name is Brian, and I'm so happy to have 33 people here listening my PhD defense. So today I'm going to defend my PhD dissertation titled Collection and Analysis of Driving Videos Based on Traffic Participants. And my advisor is Professor Atkins, and my co-advisor is Dr. Xiaoxiao Du. Okay, so to give some brief overview, my dissertation consists of 3 technical parts. First one is the traffic participant modeling in driving videos. That would include trajectory prediction and behavior prediction. And the second part would be traffic video anomaly detection. And the third part would be a smart black box for efficient data recording. Let me, okay. So to give a brief summary of my contributions and innovations, first of all, we published 3 data sets during the PhD period, one for trajectory prediction, the other 2 for traffic video anomaly detection. Second, we designed several trajectory prediction methods, including future object localization in first-person view and a bi-directional goal-based trajectory prediction. And thirdly, we have a behavior prediction work, in which we design a multitask action and intent detection prediction for pedestrians, also with the environment relation modeling. And these 2 parts would be a major part of this presentation. And the fourth one is that we presented an unsupervised anomaly detection method and also a new evaluation metric to detect the possible anomalies in the video. And this part would be a brief summary because the presentation is too long and the committee has already seen most of the contents here. And the last part is the smart black box design, and I will present a value estimation method, a buffer management method, and also corresponding experiments. So why are we interested in traffic participants? Traffic participants are vehicles, pedestrians, bikes, everything that share the road. And an autonomous vehicle system requires accurate prediction of traffic participants for collision-free planning and control. Any abnormal motion of the traffic participants could be dangerous to our self-driving car. So for example, this image shows two videos that have the participant car colliding with the Ego car. So it tells us that detecting anomalies is important for the collision warning and avoidance, but it's also important for efficient data collection and management, and I will tell you about why in the next slides. So in this dissertation, we use cameras because it's low-cost sensor and can be generalized to any type of cars. And we focus on traffic participants because we believe they are the major causation of traffic anomalies. And talking about data collection. So using the traffic video anomaly detection we talked about, we can realize an efficient data collection. So the left image shows a naturalistic driving data set, which is often used for autonomous vehicle validation and verification. The right image shows a high quality image data set for object detection, semantic segmentation, those deep learning tasks. And as you can see, the BDD 100K has way higher quality compared to the SPMD in terms of the video resolution and so on. But the data scale is way smaller because you do not have enough space for them. So it's challenging to collect high quality data in long-term driving. For example, currently the self-driving car basically generates, let's say 1 gigabytes per second data. For a year, that would go up to 2,000 terabytes. And if you have 1 million car distributed all over the world, that would be 2 times 10 to the 9 terabytes per year, which is a huge amount of data. And such data is has a low exposure rate to events of interest, meaning that most of the terabytes you used are saving just a normal driving, which is boring and not useful for autonomous vehicle validation and verification. That inspires us to design a smart black box that could efficiently collect the high quality data that can be used for the downstream VNV applications. So these are about the motivations. Before we dive into the technical parts, I'd like to introduce 3 data sets that we generated and published during the PhD period. The first one is called Honda Ego-centric View Intersection Dataset. It is basically a dataset that the videos are collected from a variety of intersections where ego car and the participant car exhibit diverse motions due to the complicated road layout and the car interactions. And the table compares our dataset with the Kitty dataset, and you can see we have way more videos, we have way more vehicle trajectories, and the dataset fully focuses on urban intersections, meaning that it basically includes the most challenging driving scenarios. And the second dataset we present is A3D dataset, which is designed for traffic anomaly detection. A3D has 1,500 videos, 18 different accident types, covers 5 different object types, and it has different weathers, different driving environments, and we have the accident start and end times labeled so that the users could train and test their model on it. And extending from A3D, we present this detection of traffic anomaly dataset this year. This is the largest dataset for traffic video anomaly detection. It has over 4,000 videos. And we provide the temporal annotations as the anomaly start and end times. In the chart, you can see the average anomaly duration in our dataset is about 3 to 4 seconds. And it also has about 4 seconds precursors so that you can detect anomalies earlier than when it happened. And it also provides spatial annotations, which are the bounding boxes and the track IDs of 7 different types of objects that are involved in accidents. Here in the pie chart, you can see most of the objects are cars, but we still have sufficient amount of other types like trucks, riders, bus, and so on. Thirdly, the dataset also provide categorical annotations, which is not included by any other previous dataset. So we have 9 ego involved and 9 non-ego anomaly types listed here in the table. And the chart shows the distribution of those different anomaly types. You can see that TC, which is turning and the crossing collision, is the major part. It's the most frequent anomaly type, but we also have a sufficient amount of other anomaly types in the data set. Here, the number is the number of videos of each anomaly category. And this image shows one example for each anomaly category. For example, here, the AH star means a head collision happened between 2 other cars. Not the ego car is not involved here. So these are the data sets we have created, and all the data sets are published and are available online. And then let's move on to the technical part. So the first part would be the traffic participant modeling in the driving videos. Let's look at these 2 figures and ask ourselves, can the ego car turn left or go forward? So the answer is clearly no, because we can predict that the white oncoming car is going forward, is going straight, and this pedestrian is going to cross the road. And in this chapter, I will introduce how our method would enable such prediction. So the first problem we solve is the trajectory prediction. Basically, we want to design models that take the observed past trajectories, capital X, the observed past images, capital I, and the observed ego motion, capital E, to predict the future trajectory sequence, noted by capital Y. And the second problem we solve is the behavior prediction. Here we split the behavior prediction as a combination of action detection, prediction, and the crossing intent detection. So in this work, we are designing our model to solve these 3 problems at the same time. Okay, so to give some related work, for the trajectory prediction, previous work focused on bird's eye view trajectory prediction, as you can see in the image on the right. And most of them are focusing on how to model the social information so that they know how the neighbor objects would affect the target object's future trajectory. Some typical work is like social LSTM, social GAN, and so on. And for the first person view trajectory prediction, most previous work are using bounding boxes or pedestrian key points to predict the trajectory. And some work uses ego motion queue as to improve the performance. And some work uses the semantic action prior and interaction modeling to improve the prediction accuracy. And for behavior prediction, there are less previous work. Many of them are studying spatial context modeling, as you can see in this image. And the specific work also focuses on extracting features from pedestrian pose, scene semantic segmentation, and object relation to improve their prediction accuracy for pedestrian behavior. Okay, so in one of our early work, we first developed a future object localization network for trajectory prediction in first-person view. This network is basically a multi-stream RNN encoder-decoder architecture, and we have a location scale encoder, which takes the past bounding box sequence and use a GRU encoder to recurrently encode the trajectory information. And it also has a motion appearance encoder, which takes the pre-computed optical flow, dense optical flow features, and use another optical flow GRU to recurrently encode information. And then the two features are merged together by an average pooling to predict the future. And we also have a separate ego motion stream, which takes the past ego motion to predict the future ego motion. The ego motion of the vehicle is represented by its yaw rate and its yaw angle and the longitudinal and the lateral position with respect to the trajectory start. And after we predicted the future ego motion, we use that as an extra input to the location scale decoder. So you can see that location scale decoder would take the predicted future ego motion and the hidden state, encoded hidden state to predict the future trajectories. So this is how FOL would work. And clearly, this is an early work and it has some drawbacks. Here we say two things are missed by this FOL model. One is that it doesn't consider the multimodality of trajectories. So for an object, given the observation of the past trajectory, we want to, there are multiple possible future trajectories because we do not know whether it wants to turn left or turn right. They're all possible. And here, the pedestrian is possible for the pedestrian to turn left, but it's also possible for it to turn right because that is actually the entrance to a building. So that leads to another missed thing, which is the goal of the traffic participant. We believe that by adding the goal, we can predict the trajectory more accurately, especially in long term. So to tackle the problem, we present a bidirectional trajectory prediction method based on multimodal goal estimation. We call it BiTrap, which is a cool name, by the way. So to realize the multimodal trajectory prediction, we built our model based upon conditional variational autoencoder. I will introduce how it looks like. So first, the model contains a recognition network, which predict the latent variable, which predict the distribution of the latent variable z, given the observation of the past trajectory, capital X, and the ground truth target, trajectory y. And it has a prior network, which also predict the latent distribution, but based upon only the observation of past trajectory. And it has a goal generation network, which takes the sampled latent variable z and the encoded past trajectory feature x sub t to predict the multimodal goal. So because we are doing sampling here, it will predict the multiple goals as long as you're doing multiple samples. And finally, we have a trajectory generation network, which would take the predicted goal and the sampled feature and the encoded trajectory feature to predict what's the future trajectory. So the CVAE contains, the CV loss contains two parts. The first part is just the trajectory loss. The second part is the KL divergence between the recognition network and the prior network. So because the recognition network uses the target future trajectory, we can only use that, we can only run that in training, not the inferencing. Inferencing, we can only use a prior network, which does not assume we know the target. So the KL divergence, what the KL divergence do is to ensure that the prior network is learned very close to the recognition network, so that during inference, even without knowing the capital Y, we still can learn some information from what the target would look like to provide a better and more accurate latent distribution sampling. So this is the how our model looks like. And for the CVAE, usually there are two ways to model the latent distribution and the target distribution. So the first way is to assume the target distribution is non-parametric, meaning that we assume we do not know how the future trajectory distribution look like. And then we assume, and then we use the Gaussian latent distribution, and we sample from the Gaussian latent distribution to predict the future trajectory coordinates. The second way is to model the target as a specific distribution. For example, here we can say we want to model it as a Gaussian mixture model. And then we need to design the latent distribution corresponding to that Gaussian mixture model. In this case, it would be a categorical distribution. So the category in the categorical distribution actually means the different Gaussian mixture model components. So each category corresponds to one Gaussian mixture model components. And we call these two methods BiTrap NP and the BiTrap GMM. And over this, in this presentation, we will compare these two to see what's the difference and what's the pros and cons of each method. Okay, so here we are comparing these two models. The top row shows the BiTrap NP, the bottom row shows the BiTrap GMM. So for the prior network, the BiTrap NP predicts the mu and sigma parameter of the Gaussian distribution, and the BiTrap GMM predicts the pi as the categorical distribution parameter. And the same thing for the recognition network. And for the goal network, the BiTrap NP model would predict the goal coordinates directly, but the BiTrap GMM model would predict the Gaussian mixture model of that goal, of that trajectory goal. And for the predictor, we use a bi-directional decoder. So it has a forward part, which is the which is the blue box. It takes the encoded feature and propagate forward to predict the trajectory at each step. The backward part will take the predicted goal and propagate backward from the goal to the current position. And we merge the features together to predict the target, to predict the target trajectory. And for the BiTrap NP, we predict the trajectory waypoint coordinates directly. For the GMM, we predict the GMM distribution parameter at each time step. And for the loss, the BiTrap NP would use a best of many L2 loss. This is because we're assuming we do not know the format of the target distribution, so that we cannot compute what's the log likelihood of the distribution in that distribution. So we can only use the L2 loss to mimic that negative log likelihood. And the loss NP consists of three parts. The first one is the goal loss. The second one is the trajectory loss. And the third one is the KLD. And for the BiTrap GMM, we do one more step. When we get the distribution, we do a forward integration and a backward integration on that distribution. So that means we're predicting velocity rather than the position distribution, and that would give us a bidirectional loss here. So the loss function of GMM consists of 4 terms. The first term is still the goal loss, The second term is the forward loss. The third term is the backward loss, and the fourth term is the chaos divergence. And in the experiment, we will compare these two methods and see how they perform. So here comes the experiment. We evaluate our methods on two first-person view datasets, JAAD and the PIE, and the image shows how the dataset look like. And we also tested on 5 bird's eye view datasets called ETH-UCY. It's a group dataset. It contains 5 subsets, and we train on 4 of them and test on the 5th to realize a cross-validation. And we also tested our method on a large-scale self-driving dataset called new scenes. And we're not showing this in the presentation. You can find it in my dissertation paper. And evaluation metrics. So our FOL is a single model prediction, and so does many previous methods. So to evaluate those single model prediction, we compute the average and the final displacement error of the predicted trajectory. And for multi-model prediction, we follow the previous work to use a best of 20 ADE and FDE. That means we sample 20 possible trajectories from the distribution and we evaluate the best one. That basically shows how well the model could cover different possible future trajectories. And we also use the kernel density estimation to fit our predicted distribution and compute the negative log likelihood of the ground truth trajectory in our predicted distribution as another evaluation metric. So here are some baselines we compare with. For the first-person view datasets, we compare with PIE Traj and PIE Full, which are the state-of-the-art methods on JAAD and PIE dataset. And for the ETH-UCY dataset, we compare with PECnet and the Trajectron++, which are 2 state-of-the-art methods just published in this year's ECCV. And we compare, and we also have a simple baseline, a single model variant of our BiTrap as another baseline by removing the CVAA part of our model. So first is the experiment results on JAAD and the PIE dataset. The first thing we see is that our deterministic method, BiTrap D, already beats all the previous deterministic competitors in terms of both ADE, CADE, and also CFDE. Second, we can see that our BiTrap NP model outperforms BiTrap GMM model in terms of the best of 20 ADE and CADE and CFDE. But the BiTrap GMM outperforms the BiTrap NP in terms of NLL. So why is that? You will see the discussion in the next experiment. So in the bird's eye view experiment, we use ETH-UCY data group. It consists of 5 datasets called ETH, Hotel, Univ, 01, and 02. And here we can see that both of our methods outperforms the state-of-the-art methods on most of the datasets. And also BiTrap NP outperforms BiTrap GMM in terms of this ADE and FDE, similar to what we have seen before. And as to the NLL, we can see that the BiTrap GMM outperforms BiTrap NP, also similar to what we have seen before. So why is that? We believe this is because the BiTrap NP uses the best of many L2 loss, making it has a better ADE-FDE results because ADE-FDE is basically a best of many L2, right? And the BiTrap GMM uses an NLL loss, making it has better NLL results for sure. So it seems that in terms of different evaluation metrics, we have different performance. And this also shows that the BiTrap NP tends to predict a more diverse distribution so that it has better chance to cover different future trajectories. But the BiTrap GMM intends to predict a more compact distribution so that it doesn't cover everything very well, but the NL is generally better than the NP model. And you will see the visualization in the qualitative examples. And here we also show the per step and our results, because we hypothesize that our model improves the long-term prediction. And here in the images, we compare our method with the Trajectron++, and you can see that after 2 seconds, our model outperforms Trajectron++. It proves that our hypothesis that the bi-directional model could perform better in longer-term prediction. Okay, so here are some qualitative examples. I'm gonna skip the first one. So let's look at this image, and this exactly shows what I talked about. So the BiTrap NP predicts more diverse future trajectories, so that it covers many trajectories. So here, for example, in figure D, you can see that the past trajectory is blue, the future trajectory is red. So basically the pedestrian goes forward and then suddenly turn back. And the BiTrap NP could cover that. But the BiTrap GMM obviously predicts a more compact distribution and is not able to cover that trajectory that BiTrap NP was able to. So, so this shows how our methods achieves the state-of-the-art performance on many datasets. But we are still not sure how it would perform in a robotic application, because we are robotics researchers, right? So we add one more experiment about robot navigation simulation. So we did that in a simple way. We grabbed the ETH-UCY datasets. We replace one human in each ETH-UCY scene with a robot, as you can see in the right image. So there's a robot in the middle and 4 pedestrians surrounding it. And the red star shows the goal of that robot, which was the goal of the pedestrian who was sadly replaced by our tiny android. The robot would generate 100 random paths with a naive Bayesian curve. We use naive way because we're not doing path planning research anyway. And the robot has a trajectory predictor equipped on board, either a BiTrap NP or BiTrap GMM, so that it can generate cost map, as you can see as the heat map on the right. And the cost value is basically the negative log likelihood of a position that will be occupied by a pedestrian in the future. In this way, we can compute the collision confidence of the random path, and we can find the safest path among that 100 random paths. And then we can evaluate our trajectory predictor based on the safest path collision rate and the collision detection AUC and average precision. So the first column of this table shows what if we randomly select one path from that 100, what would be the collision rate? And you can see that by using BiTrap NP and BiTrap GMM, we successfully reduced the collision rate by more than 50%. And we can also see that the BiTrap GMM outperforms BiTrap NP in this experiment, because remember that we are computing the cost map using distributions, and the BiTrap GMM is predicting more accurate distributions based upon the lower NLL metric, as we saw in the experiment. So it's consistent with what we observed. So yeah, this part concludes our research in trajectory prediction. And then we're moving on to the next part, which is the behavior of the pedestrian. So the behavior prediction actually answers the question, what is the action of the pedestrian? What is the intent of crossing street? So we hypothesize that intent is basically the willingness to do some action in the future. So if we can predict the future action, it should be able to help the intent detection. For example, here, if we can predict that the future action of this pedestrian is walking towards the crosswalk and the crossing, then we should be able to detect that the intent of that pedestrian is will cross. And we also believe that adding some environment information should be able to help us predict the intent of the pedestrian more accurately. And so to tackle both of these problems, we present a multitask pedestrian behavior prediction network. The network contains a visual feature extraction, which is a pre-trained deep convolutional neural network that takes the cropped image surrounding the pedestrian and get the deep image feature. And it has the trajectory feature extraction, which is a fully connected network that embed the past bounding boxes to predict the trajectory feature. And these features are concatenated and sent into a RNN encoder, which will detect what's the current action and intent of that pedestrian. And we also have a future action predictor, which takes the encoder hidden state to predict the future actions. And the hidden feature of that action predictor will be collected and used as an extra input here to the encoder, so that the encoder would have an extra input from the future prediction. This is similar to the temporary recurrent neural network model that published last year. And our model also have a attended relation graph to model the relations between the target pedestrian and the surrounding traffic objects. So we use separate networks to model the traffic participants, which are the cars, pedestrians, and the traffic lights, and the traffic signs, and the crosswalk, and also the station. A station is a bus stop or a train station, and so on. And we also have the ego cars motion. So because we do not, because each traffic participant does not have a constant number of instances. For example, there could be multiple cars or pedestrians. We use a soft attention module to learn what instances are more important than the others. And this is how the soft attention module looks like. It is basically taking the combination of the observed features and the encoder hidden state and predict a weighting vector and compute the weighted sum over the instance belongs to this specific type. And those features would be concatenated together to formulate a relation feature, which is another input to our model. And we test our model on PIE dataset. So to evaluate the intent detection, we use accuracy and F1 score, similar to the previous work, but we also found that accuracy and F1 score is not enough because the test dataset of the PIE is actually imbalanced. So we propose to use AUC and score difference as a supplement. The score difference is basically the difference between the average score of the positive predictions and the negative predictions. And we want the score difference to be bigger. That means the model could distinguish the positive and negative better. And for action evaluation, we simply show the mean average precision over the anomaly, the action categories. For the PIE dataset, there are 7 different action types and the 2 different intent type, which is just will cross and will not cross the road. And we compare with 2 baselines. One is naive one, which is simply classifying all the samples as positive. And we will show why this experiment is important later. And the most important baseline is the PIE intent, which is the state-of-the-art method published with the dataset. Okay, so if you look at the table, the first thing we would observe is that the naive one has high accuracy and F1 score, even compared to the state-of-the-art PIE intent. This is because the data is imbalanced in the PIE test set. So that means the accuracy and the F1 score meaningless. And that's why we need to use AUC and delta S as an important supplement. So if you compare our ablations, we will see that adding the action detection and the future action prediction could largely improve the intended detection AUC and the delta S, which is consistent with our hypothesis. And adding future module also improves action detection MAP. And if we add the relation module, it could largely improve the AUC and delta S again, meaning that knowing the surrounding environment actually helps a lot of predicting the pedestrian's intent. And now we want to study among all the different traffic objects, which ones are more important than the others. So here, if you look at the green rows, you will see that crosswalk and traffic lights are two important factors for intent detection. Adding them are largely improving our AUC and delta S. But the rest of them are not necessarily helpful by themselves. That makes sense because sometimes the traffic neighbors are just not related to the objects and the target objects, but we have no way to learn that very well, and so does the traffic sign and the station and the Ego car. So, but combining all of them together would give us our best performance, meaning that if we only know one type of traffic objects, it could be not enough. But if we put everything together, it could be a better information embedding. And in the future work, it also inspires us to do more about how to extract useful information from the environment. And here are some quantitative examples. So we can see that the future action module significantly improves the performance of intent detection here. And all methods get performed better with closer object. That is quite straightforward because getting closer to the object gives you higher resolution images. So there are many challenging cases in pedestrian intent detection. For example, here, the person looks like he's going to cross the street, but he's actually yielding the oncoming three people. And our method could accurately predict that the pedestrian is not going to cross, but some baseline methods are not performing very well in this case. Because our model have a future module, so it knows that in the future, the person is actually not crossing the road. So case 2 is that a person is standing there facing the road, but is actually waiting for a bus in the bus station. And case 3 shows that the person was firstly facing the road, so we have a very accurate prediction. But later, when we get closer to her, she's actually turning her face to another direction, which confused our model to predict the wheel cross intent. So these are showing us that modeling the pedestrian intent is still a very tough problem and still need more further research. Okay, so that would conclude our first technical part. And we will jump to the second part of the traffic video anomaly detection. Okay, so I will give a brief summary here. The traffic video anomaly detection basically takes a video and detects and computes an anomaly score for each video frame. So here is an example of the video that contains anomaly, and the dash curve shows the ground truth annotation. The solid line shows the scores computed by our method. And here we present a unsupervised video anomaly detection method based upon our FOL work. So basically we predict the future object bounding boxes first, and then we compute the anomaly score by the prediction consistency, which is represented by the standard deviation of our prediction over time. So our hypothesis is that if an anomaly happens or going to happen, the consistency would be bad. The model would not be able to predict the bounding box accurately and consistently. And based upon FOL STD, we present a FOL ensemble method which combines our method with a state-of-the-art frame-level video anomaly detection method called Anomaly. And we'll skip the detail about that work. And in this work, we also proposed a spatial temporal area under curve as an extra, as a supplement to the existing VAD evaluation. Current VAD work used AUC to evaluate performance, but AUC cannot evaluate whether the model is looking at the correct location in the image. So here we compute ST-AUC by first compute the true anomaly region ratio. The TAR is actually a ratio of how much of the anomaly score we computed locate within the annotated anomalous region. That's a value between 0 and 1. In the best case, it will be 1, but it will never go to 1. And given the TARR, we could compute the spatial temporal ROC curve, which is shown on the right. And you can see that spatial temporal ROC curve is always lower than the original ROC curve because it measures that our model is not fully looking at the true anomalous region. And given this ST-ROC, we can compute ST-AUC. And here are some experiment results on our DOTA dataset. As you can see, the FOL ensemble method outperforms all the competitors in both AUC and ST-AUC metric, meaning that this method can detect the can accurately detect the start and end time, but also accurately detect the position of where the anomaly happens. And this table shows the per class AUC and ST-AUC, and we can see that for some anomaly classes, the there is a big gap between the AUC and ST-AUC. That means the method accurately predicts the start and end time of the anomaly, but it's actually not looking at the correct anomaly region. So that shows why the ST-AUC is very important. Okay, so the third observation is that simply the ego-involved anomalies are easier to detect than the non-ego anomalies. This is just because the ego-involved anomalies usually happen very close to the camera, so the visibility is better. And we also conducted action recognition and online action detection experiments on our datasets, but I will skip the details here. The readers are encouraged to read my dissertation paper or journal paper to find the details. So this concludes the video anomaly detection work. And we're moving to the last technical part of my dissertation, which is the smart black box design. So the smart black box design is actually enabled by our video anomaly detection. It is an intelligent event data recorder that compresses and records high bandwidth data according to data value and onboard storage. So in this work, we present an SBB system pipeline and the data value estimation method and a buffer management system and a local buffer optimization method for to find the best lossy compression factor, and a prioritized long-term data management for the limited onboard storage. Okay, so this diagram shows the SBB pipeline. So we capture the data from the raw data from sensors, and we run our deep learning models on it to detect the events. And then we can estimate the data value and the similarity between the data frames. And then a deterministic Mealy machine is used to determine when should we start to buffer data, when should we wait for seeing more data, and when should we terminate and pass the buffered data to the downstream functions. So the deterministic Mealy machine would pass a buffer to the compressor, and the local buffer optimization would compute what is the best compression factor that we should apply to that part of data based upon data value. And then the compressed data would be sent to the storage, which is the priority queue. And then if the SBB has the internet connection, it would be able to upload the data to the cloud database and delete it from the car so that it can save the storage for the next data collection experiment. Sorry. So so it seems that the key of our smart black box is how do we find the best compression factor. So we formulate this local buffer optimization. which is to find the compression factor for each frame in the buffer to realize an optimal trade-off between the storage cost and the recorded data value. So here comes the LBO objective function. So what it does is to minimize the storage cost, to maximize the data value, and also to maintain the continuity between the continuous data frames. Okay, so storage cost is simple, and so is continuity. But how do we compute the data value? Okay, so recall that we have talked about video anomaly detection, and we have talked about online action detection. So we are computing our data value using the anomaly scores from BAD and the anomaly classification confidence score from the OAD. Okay, so we have two methods to compute the data value. The first one is the weighted sum between these two. Let V denote the data value. The first term is the video anomaly score. The second term is actually a weighted sum of the negative log2 of the frequency of each of the anomaly category that the data belongs to. So the second term is actually similar to a expectation of the information measure of that random variable. The second way to combine the BAD and OAD is to use an independent Bayesian classifier combination, because these two are classifiers. And what we do is that we estimate the posterior probability of data value V given the anomaly score and the anomaly classification. We assume all of them are random variables generated from categorical distributions with dirichlet priors. And then we can iterate over our data set to use the IBCC to learn what's the posterior distribution. I will skip the mathematical derivation here. And finally, our data value is estimated as the expectation of the V equals to 1, meaning that V is an anomalous data. Okay, so we will compare these two as well in our experiment. And now we have data value estimation, we could solve this LBO objective function to realize the compression factor selection. And once we have all the buffers saved on board, and we have a new buffer that we want to save, we will have a priority buffer recording strategy, which would pop and discard the low value data from our priority queue and insert this new data into it. So that eventually the storage is only used to save the newest high value data. And we conduct simulation experiments first. I'm going to skip this simulation experiment and jump to the real world experiment. So to test this SBB in real world data is difficult because there's no such real world big data that contains anomaly in the middle. So we have to create a fake one. So what we did is that we take 10,000 videos from the BDD 100K and randomly select 500 videos from DOTA and then combine them together. That would result in a single long video for more than 100 driving hours, more than 700 gigabyte size with HD resolution. The video contains 4 million frames, and the 0.5% of them are anomalous frames. And we run our SBB on this data to see how it can save the space for saving the data. So you can see that the total space of the data cost is reduced from 705 to 112 gigabytes. And that number will go down to 19 gigabytes if we have ground truth label of the anomaly. Because the VAD and OAD is not perfect, sometimes it just cannot find anomalies, or sometimes it would classify normal as anomaly. And the space ratio of the anomalies would increase by 100%. And if we have ground truth label, that would go up to 2700%. which is a huge improvement. And with limited onboard storage, we can see that the SBB could save 25% less normal data, but 50 to 100% more anomaly data than a simple first in, first out data recording strategy. So that means we are removing more normal data to save space for the anomaly data. Okay, so so we also compare different value estimations here. So for example, we can see the VAD distinguishes the normal and the anomaly better than the OAD, as you can see by the difference of the decisions between these two. And the weighted sum strategy has a bigger decision difference between the normal and anomaly compared to the IBCC combination. But the IBCC has a way lower standard deviation, indicating that it's making more stable decision. So, so it's selecting the different value estimation and the hyperparameters really depends on how the users want to use the SBB. For example, if you want to collect a specific type of specific type of anomalies, then you should use OAD or the combined method and put more weight on that specific anomaly types. But if you wanna record general type of anomaly, no matter what it belongs to, you should use the VAD-based value estimation because it doesn't consider what kind of anomaly it belongs to. Okay. And here we can see that for some anomaly types, the SBB could capture it very well. For example, here you can see the AH ego, non-ego, the LA ego, the OC ego, and non-ego. We have a very high decision on those data, which means that the SBB tends to maintain a very high quality for those data. But for some anomaly types, the SBB just didn't capture it very well. Here, most of the VO and OO are considered normal, so they are highly compressed. So that means that the SBB performance highly depends on the performance of the VAD and OAD we did in our second chapter. And to improve the SBB performance, we need to improve the video anomaly detection first. Okay, so to draw a conclusion of the whole dissertation, it's faster than I expected though. So we first presented trajectory prediction work in both first-person view and bird's-eye view, and we also presented a multi-model prediction network with the goal estimation. And we have 2 papers for this part. And for the pedestrian behavior prediction, we present a multitask action detection and prediction and intent detection network. And we also modeled the relation to boost the performance for intent detection. And for video anomaly detection, we present the trajectory prediction, consistency method for anomaly score computation, and we present a new ST-AUC metrics as a supplement to the current research community. And there are also 2 papers going out there. And for the smart black box, we present the smart black box pipeline, we present a buffer management, a local buffer optimization method, and we also conduct thorough experiments in simulation and real world. And 2 papers are talking about this, this part of my dissertation. Okay, so I would also like to point the readers to some future works. So first, I would like to develop some explainable and transferable interaction modeling. So as you can see that we are adding relations to the environment, but we do not know how well it learns the interaction. We only know it can improve the intent detection or trajectory prediction. So we want to make this part explainable. And second, we want to apply the trajectory and the behavior prediction to our motion planning of the autonomous vehicle so that eventually we can drive the car safely on road. And for the VAD, we want to increase the VAD accuracy leveraging supervision because we found that the unsupervised method has some maybe limitation. So if we want to actually apply the VAD to any real world application, we need it to be way more accurate than the current 70-something accuracy. The last future work would be adding some dynamic metrics for the better compression decision making in the SBB, so that the smart black box could make wise decision in changing environment. Okay, so I did not expect no interruption here, so I'm going to the acknowledgement part. Sweet. So first of all, it's my pleasure to, it's my honor to sit here and present my work to you guys. The very first person I want to thank is Professor Atkins, who has been guiding me for the past 5.5 years, and also my lab mates who helped me a lot in the very tough period that I did not have any research fruit at that moment. And I also want to thank colleagues from FCAV, especially Professor Ram Vasudevan and Dr. Xiaoxiao Du, who provide a lot of brainstorm with my research on the pedestrian intent and trajectory prediction. And the most importantly is my wife, Xinming, who is also listening right now. We have been together for like 5 years, and it's been a long journey, and she has been there all the time to support my research, support my life, and she's all my motivations. And so is my mom, who is in the middle. This is actually a picture we took in the wedding we just had this summer. It was a tough quarantine period, quarantine time, but we still had some valuable memory together. And without these two women standing there, I would not be able to sit here. I would not be able to show whatever I have done. I would not achieve anything. So thank you so much. And I would also like to thank my colleagues in Toyota Research Institute and Honda Research Institute, and also my friends in my basketball team and in Robotics Institute. And these are valuable memories, and I will not forget them for the rest of my life. I would like to send special thanks to Mingze, who I'm not sure if he's here, and also his advisor, Professor Crandall, who helped me a lot with my research in video anomaly detection. And I would also like to thank Nan from Professor Komanovsky's lab. He is like an older PhD student who helped me a lot in the early year of my PhD, go through the confusing time. So, well, this is the last page of my slides. It's kind of awkward that I'm the only one who's speaking and no one is showing anything, but I would like to thank everyone who come today. And I would like to thank my old man in this image, the first Dr. Yao in the family, and hopefully I can be the second one. So yeah, cheers everybody. Thank you. That will be the end.